In this episode of Woodlands on the Web, we'll be looking at reaction rates, rate laws, and orders of reactions. So reaction rates are based on the decay of reactants and the formation of products. Here we're looking at bleach having been added to a yellow dyed solution. And as you can see, it's growing gradually paler and paler until eventually it's going to be totally clear. So applying some knowledge of kinetics and how things decay or get formed would allow us to figure out what's going on in that reaction vessel. These are the formulas you have available to you regarding kinetics on your AP chemistry reference sheet. So here's a typical curve showing the decay of reactants and the formation of products. The reason they're curves are because you have continuous reactant decay, so this is going down. At the same time, you have continuous product growth or formation. So eventually there will be zero reactants left and only products left in the reaction vessel if it's not a reversible reaction. Okay, so our general reaction rate equations can be written as the loss of the concentration of reactants over the change in time. Or we can talk about the positive occurrence or formation of product concentration over change in time. The main thing is that your reactant values are going to be referring to something that's less than zero, and your product values are going to be a positive number. So the general form for a typical chemical reaction, and this is referring to elementary reactions only. We'll look at multi-step reactions in a later video, but you can talk about any of the different substances within the chemical equation. So for example, if we're talking about things with respect to reactant A, it's going to be the loss of the change in the concentration of reactant A over the coefficient goes in front here, referring to how much it's going to be multiplying the time by. Okay, that's going to be true for the change in reactant B. So again, that's a negative value. We have little b delta t on the bottom. And the main difference here is that we're going to leave the negative sign off for the concentration of C and D because those are our products. Okay, so again, the lowercase letter is the coefficient of the substance in the equation, and the capital letter is referring to the substance itself. Okay, because we're talking about the loss of a reactant or the gain of a product, the rate of reaction is always going to be a positive value. And they're all going to be equal to each other with respect to each individual species. Okay, again, we're going to treat each species independently. So if we have an equation as shown here, then we can write our rate of reaction with respect to any of those species. I would suggest you pause here and try that for yourself real quick. So if you filled in and followed the steps that we did above, or the relationship that we talked about above, you should have the following rates. So again, all of these rates are equal to each other because it's talking about substances or species in the same chemical reaction. Okay, so again, the only difference here between what we did here and just before this is that we have coefficients that are numbers instead of representative letters. All right, so looking at trying to figure out the average rate of this reaction. So we have information given to us here that's regarding reactant B. So that means we're going to want to use our rate expression for reactant B. So we basically, based on the data that we're given, we measured the concentration at two different time points of reactant B. We'll talk about how we can do that later, but one of the most common ways is if the reaction has a color to it and you're looking at the color change using spectroscopy or spectrophotometry. But if you would, so take the expression for species B and try plugging in those values and see if you can get the same average rate that I do. So pause here and try that real quick. So if you had a little trouble with this one, the main thing to remember is that when we're talking about change of anything, it's always going to be our final minus our initial thing. So in this particular case, you're going to have the negative of 0.0357 molar minus 0.1000 molar over 3 times 20 seconds minus 0 seconds. Okay, when you solve that and you simplify that expression, you get 1.07 times 10 to the minus 3 molarity per second. I think it's worth noting that that's possibly going to be written as, or in a few different forms. So molarity per second, I'm going to write this down at the bottom real quick. Okay, you have it written this way. That's the same as saying moles over liters times seconds. So another way you could see that, and the way that you would often see this written in terms of College Board expressions, is you would see it written as moles times seconds times inverse liters in this particular case. But that's referring to molarity per second. So change in concentration per second. Okay, so the next part is going to be to predict the change in concentration of substance D during the first 20 seconds of the reaction. Okay, so again, based on our initial statement about the average rates, we can tie those two together since we've already found the rate of reactant B loss. We have that we can use to determine the amount of product D formed. So pause right here, see if you can figure out what to do, and then take a minute and you can hit play again. Okay, so given the expression that we wrote for the average rate of product D formation, I'm going to rearrange this to solve for change in delta D concentration, or change in substance D concentration. So my working equation is going to be the change in concentration of substance D is equal to the rate times 2 times the change in time. Okay, so that means that my change in product D concentration is going to be the rate that I already found, because we already said before that all of our rates are equal to each other. So 1.07 times 10 to the minus 3 molarity per second times 2 times 20 seconds is how long is passing in this given point. So when I solve for that, notice my seconds divide out to equal 1, so I am left with a concentration, and that concentration comes out to be 0.0428 molar. Okay, so that's the change. So the answer to the question, it's because it says it's during the first 20 seconds. Okay, so you want to ask yourself, how much product D did I have at the beginning? Okay, so again, this value is the change in the concentration of D. But because the concentration of D at time 0 is 0, then 20 seconds later, the concentration is 0.0428 molar. Okay, and as it says at the bottom here, reactions occur as a result of reactant molecule collisions. So in a next video, we'll talk about collision theory again. So now let's get to where we can actually talk about rate expressions for single reactant types of reactions. So if you think about it, the only type of reaction we've really seen that sounds like that is when you have one substance that's turning into products. So that means that these are typically decomposition reactions that this is referring to. So the rate is a lowercase k. Notice that this is not capital K, so it's not the constant of equilibrium or anything like that. It is a rate constant, lowercase k. And that's going to equal the concentration of the reactant raised to some power, which is going to represent the order of the reaction. Okay? The reaction order is not based on the chemical equation, and you have to determine it experimentally. And this is going to be for specifically non-elementary reactions. Okay, so take a quick second and read the question that's shown here. This is from the Masterton text, and read the problem and look at the data that you have, and then we'll talk about moving forward. So pause it real quick and read the question, please. So in this problem, we're looking at the decomposition of acetaldehyde based on this given rate equation. So there are a couple different ways you can solve this. One of those would be algebraically, which, as it says here, is the hardest way. I'm going to show you why this works, though, and then I'll show you the easier way, which is justified by the algebraic way. Okay, so the algebraic way would be comparing the rates of two trials. So you'd have rate 2 over rate 1. And we do have our rates given to us. Notice that that is moles per liter times second. So that is basically molarity per second, like we had in our previous example. And my little dot keeps coming out. Okay, so we have two rates. So based on what we had, that's going to be our concentration raised to the power of m. Okay, so we have our our second rate is going to be the rate 2, the concentration at time 2, or over the concentration at time 1 raised to the m power. Okay, if we're using the first two trials here, so trial 1 and trial 2, then what we would be getting is that our rates, 0.76 over 0.34, is going to be equal to 0.3 over 0.2 raised to the m power. Okay, our rates come out to be 2.2 when we divide. So in order to algebraically solve that, because we have something raised to a power, we do have to use logs. So you can use the log of 2.2 equals m times the log of 1.5, which is what 0.3 over 0.2 comes out to be. And then you end up getting something roughly around 1.9, which you can say is roughly 2, and therefore this is going to be a second order reaction. Okay, the order of reaction is basically talking about how quickly the rates are changing. Okay, but let's look at this observationally because that really is the easiest way to do it. The main thing you want to look for are trials where concentration either doubles or triples or multiplies by some obvious factor. In most cases, you're almost always going to be given data that has a doubled factor somewhere. In worst case, a tripled factor. Okay, so let's talk about why that's important. We're going to use trial 1 and 3 here because we're changing the concentration from 0.2 to 0.4. So if we use that information, then we're comparing the concentration of these two trials, 0.2 molar versus concentration for 0.4 molar. And we can see that the rates are therefore 0.34 versus 1.4. All right, if we divide those two rates, so in this case, we're taking rate 3, which is 1.4, the rate for trial 3, over the rate for trial 1, and right there we get roughly 4. Okay, because our concentration has doubled, then we can say that that's going to be the same thing as saying 2 squared. And therefore, the exponent for that is going to tell us that this is a second order reaction as well. Okay, so you're basically doing the algebraic process, but you're simplifying it for yourself by using something that's observationally going to be obviously doubled or tripled, but doubled is generally the easiest. So when things get a little bit more complicated and you have elementary reactions that have more than one reactant, then you're still going to have some rate constant K, but you're going to have to take into account the reactants in the equation. Okay, so those are going to be raised to their own order. Okay, go ahead and pause and copy down the steps for the reaction order with the 2 or more reactants, and then we'll wrap this up with when we're looking for linear graphs. Okay, I'm going to explain this further in the next video, but when you're looking at a 0 order reaction, then the graph is going to be linear when it's your concentration versus time. If it's linear when the natural log of your concentration versus time, then that's a first order reaction. And if it's linear when your concentration is the inverse versus time, it's a second order reaction. The reason is calculus. In closing, I hope that at least gets you started on reaction rates and rate laws. Thanks for watching.